second or two. Okay,
There.
great. Thanks very much.
Thank you. Yeah, I don't remember what title I originally suggested, but this is the title I could remember. Let's see. Can you guys see my screen yet?
Nope, not yet.
Oh.
We're not seeing it. Oh, there it is.
There it is. Okay, good. Yeah. So somehow this is working better than last week. I'm very pleased. I can actually see. I can actually share my screen. So thank you for inviting me. It's been fun to listen to all these talks. So I want to tell you about some work that's joint with Michael Landry and Sam Taylor on flows, growth rates, and veering triangulations. So so what is this actually about? So the subject is kind of the subject of flows in three manifolds. That's kind of where we're starting. So you'll see in a minute, if you have a three manifold and you have sort of a flow inside the manifold, you can do various things with it. One of them is to kind of study dynamically, study the rate of growth of closed orbits, how many closed orbits there are of a given size. And that's a sort of an entropy measure. You can study transverse surfaces in the manifold to the flow, and I think this is probably a familiar set of things to think about. So it goes back to various people, but in particular, one should mention Thurston's study of foliations and vibrations, and Fried, and work of Gabay and Mosher and Fendley. So we're in a minute going to talk about Suranasov flows, and that's the setting I actually want to talk about. And that's the left side of the screen, and on the right side of the screen, I have the words metric graph. So this is a set of kind of tools and techniques that we want to apply to study flows in the three manifolds. So here we have a directed graph and you should imagine that the edges have lengths, and then you again can study the growth of cycles. You can count the number of cycles in the graph of a given length, and you can study the growth rate of that. And this is mediated by something called Perron polynomial, which I won't talk too much about, but it will sort of feed into what we want to talk about, and was studied kind of in this sort of context by McMullen, but I think it goes back much further than that. It's also part of dynamics kind of in general. And then the connection between these two things, the ability to kind of use the graph to code the behavior of the flow, it's also an old idea, but in this context, there's a very concrete tool for doing it called the veering triangulation, which was introduced by Egel and then generalized by Egel and Gary Tow to this context I want to talk about. So I'll talk about that in a few minutes also. It's a kind of canonical triangulation of the three manifold, which can be used to give a very concrete tool for studying the kind of questions we want to study. And in fact, so that it doesn't kind of become too abstract and so on, let me take a kind of motivate the discussion by a particular question which comes up. It was suggested to us by Chris Leininger, but maybe I don't know if it's been asked separately, but it's the following kind of natural question, and in the setting of a fibered three manifold. So imagine you have a hyperbolic three manifold that fibers over the circle, and there are many fibrations typically. Maybe I should emphasize that if H1 of M has dimension, has rank bigger than or equal to 2, then there are either 0 or infinitely many fibrations. So we'll come back. So this is Thurston's theory of the Thurston norm in fibered manifolds. So there are many, many fibrations, and for each fibration, we'll just name them Xi for the moment, there is a dilatation of the fibration, which we'll come back to this number. That's kind of the subject of the talk. But for now, let's just think of it as the expansion rate of the monodromy map when you go around the fibration. So you take a fiber of the fibration, you push it all the way around the manifold, you come back, you get a map from the surface to itself, and the Teichmüller dilatation of that map is lambda, or I guess log of lambda is the Teichmüller translation distance. So that's a number associated to every fibration. And you could look at the set of all such numbers over all fibrations for that given manifold and ask, what is the closure of that set? It's a set of real numbers, greater than or equal to 1, well, greater than 1. And you can ask, where does it accumulate? What's the structure of this set? So that's Leininger's question. And by the end, I hope I will be able to say a little something about kind of an answer to that question. Okay. Please stop me and ask questions if I'm going too fast. I'm not very good at calibrating 30-minute talks. So pseudo-Anosov flows. What's a pseudo-Anosov flow? So it's a flow. You have a manifold. So M bar here is going to be a closed 3 manifold. The bar is there because when I want to take off the bar by removing the singular orbits. But so I have a flow. Here's one line of this, one flow line of the flow. So being pseudo-Anosov means, first of all, most places it's Anosov, and being Anosov means that there's a pair of foliations of two-dimensional foliation. So here's this red leaf over here is one of the two foliations, and in one of the foliations, they're both invariant by the flow. And in the red foliation, the flow lines are asymptotic to each other. So if you look at this particular blue one that I started, all the in the red leaf through the blue flow line, all of the other flow lines converge to it in forward time at some definite rate. Because of compactness, it has to happen at a definite rate. And then the green foliation leaf through this flow line consists of, I guess I didn't draw them. Let me draw them. It's flow lines which diverge away from the blue one, which is another way, or you could just say that in backward time they converge to it. So it's expanding in the green directions and it's contracting in the red directions. That's Anosov. And then I said it's Anosov off of some bad set. So there's a finite union of singular orbits. And at a singular orbit, we have what we've come to be familiar with from pseudo-Anosov maps. We have, so here's a flow line that's singular. And in a neighborhood of this, let's see, how does one think about this picture? So at the bottom of this picture is the little cross section. So you see this little red tripod. That's how the red foliation leaves come here. So there's a kind of the blue line is a branch line for the red foliation. And it's also a branch line for the green foliation, which I've drawn a little bit of over here. And that's the standard picture, right? There's still expansion in the red and contraction in the green, or vice versa, I guess. And so that's a pseudo-Anosov flow. It's kind of the suspension of a pseudo-Anosov homeomorphism, at least locally. Okay, any questions about that? And there are many of these. The standard kind of motivating example is the fibration. Whenever you have a fibration of a 3 manifold around a circle, and the monodromy is pseudo-Anosov, then the suspension, so kind of the suspension flow of a pseudo-Anosov homeomorphism of a surface is the kind of reason for the existence of this definition. But there are many more such flows. Okay. All right, so that's the flow. Now I want to talk about growth rates and of cycles in the flow. So in order to have a growth rate, you have to measure the length of the loops so that you can decide what you're counting. And one way to do this is to pick a cohomology class in the manifold. So suppose you have a cohomology class in the manifold, which we think of as a closed one form. I should write closed. And I want to consider the ones that are non-negative along the direction of the flow. So that's the condition here. If I have a one form which is non-negative along the positive tangent vectors to the flow lines, then I call it a positive form. There's a kind of cone of such in the cohomology. You should expect there's a sort of a cone of such forms because the condition of being non-negative is a convex condition. And then once you pick one, you can compute a growth rate with respect to this form. And that's just the following thing. You look at the set of all orbits of the flow. So these are directed orbits, closed orbits. And for each one, you compute the cohomology class evaluated on that orbit, which is the same thing as the integral of the form along the orbit. And you look at the ones that are less than or equal to a fixed t, and you count them. And then you take that and you raise it to the power of 1 over t and take a limit. And that will just be the growth rate. That would be like thinking of this. If this quantity is roughly lambda to the t, then this process extracts the lambda. So lambda is the kind of exponential growth rate of this growing set of things. And an important special case is one in which if so we started with the pseudo-Nassau flow. If you pick a transverse surface to the flow and take its Poincare dual, that's just the cocycle that counts intersections with the surface S. You can turn that into a form which is positive on the flow, and in fact, anyways, and then what we're doing, so for such a thing, we get a cohomology class which is integral, and we can compute growth rate with respect to that. And if that, and there are kind of two cases, one of them has been studied a lot, and the other one not quite so much. If this green surface S intersects every flow line of the flow, then this is just a fibration. Then you follow the flow around and you come back to S, and so you get exactly the structure of the fibration. So S would be a fiber of the three manifold, and you can study this quantity for that fiber, and that's exactly the Teichmuller dilatation I was talking about before. It's the same thing. So this was studied by Fried and McMullen, and I won't give the details of this, but it's a well-behaved function. You think of this function as a function of a point in the cohomology in that cone. One can study what it looks like. It has some nice properties. But now, if it isn't, so suppose that S, what does not mean here? Suppose S does not meet every fiber of the flow. So maybe in sort of cartoon form of this is that S is some surface inside the three manifold. There are various leaves that it's transverse to the flow. So every leaf, the leaves kind of cross it whenever they cross it, but there might be somewhere else in the manifold a bunch of flow lines that never meet. So there's some picture that looks like this, maybe some kind of complicated, perhaps part of the flow where there are flow lines that never meet S. Of course, there are flow lines that go from this part and eventually do meet S, but there's some kind of a core thing that avoids S. That's possible. And when you do that, we take the flow and we maybe use this notation for the part of the flow that avoids S, just this kind of piece that I took over here. And on that part of the flow, our one form should give 0, because when you run around the recurrent part of that flow, you can't accumulate any intersections with S, and so the one form will vanish there. And that means that the growth rate will be infinity in that case, because there are infinite, as long as something interesting is happening over here in the complement, there's lots and lots of cycles that avoid S, that have value less equal to 0, and so the growth rate becomes infinity. So that's not all that interesting to do other than to remark this fact, but we can, instead of giving up, we can look at, we can try to study this a little further. We can take another one form. This time it can be just in the complement of the surface S, right? On a smaller three manifold, there might be more cohomology classes. So take another one, which is still positive on the part that's left of the flow, and you can ask what is its growth rate, okay? And so that's kind of that's the point of view I want to promote here, that you can kind of zero in on subsets of the flow and study their entropy or their growth rate in a useful way. Okay, so what is the tool that I want to talk about for doing this, for actually carrying out some kind of computation? That's the thing I said in the beginning, the Egel-Gueriteau veering triangulation. And I often, one can spend a long time describing the ins and outs of how one builds this triangulation. I want to just give a kind of quick overview of where it comes from and explain why it's canonical. So we have to start with a pseudo-Nassau flow, which we already have. It has an extra condition, which due to Fenley called not having perfect fits. And I'm not going to say what that is. It's not, it comes in the fine print of the construction. And since I'm not going to talk about the fine print anyway, I'll just say that there's an extra condition. And then we build a canonical triangulation in the following way. You start with, you take the universal cover of the three manifold, and you lift the flow to the universal cover. And then if you mod out by the flow, so mod out, identify every flow line to a point, then your three manifold, your universal cover becomes a surface, and that surface is called the leaf space. And it in fact is a plane. Topologically, it's a plane. That's a theorem of Fendley and Mosher. So you can think of, all these flow lines in the universal cover are all moving kind of upward and together like this, and you can think of a kind of planar cross section of all the flow lines as the leaf space, and that leaf space is therefore endowed with the images of the two-dimensional foliations, the two-dimensional stable and unstable foliations that we drew in the beginning, the expanding and contracting directions, give us one-dimensional foliations in the leaf space, and that's what these red and green lines are supposed to be. So you have these singular foliations. The singular points actually play an important role. And I want to look at the structure of that leaf space. And here's the idea. You look at inside this leaf space. You look at foliated rectangles. So just consider drawing foliated rectangles in this kind of way. Locally, you can of course draw many of them, but you can imagine kind of trying to make them larger and larger until they sort of hit a singularity. And at that point, you can't continue. Once you hit a singularity, you can't build anything bigger than that. It won't be a foliated rectangle, at least in that direction. So here are three. So the triangulation that Egel and Gerito build has the following pieces. And let me draw it here. The edges of the triangulation, actually, this is the universal cover of the triangulation. The edges are rectangles that have pairs of singularities at their opposite vertices. That's an edge. A face, a two-dimensional face, is a rectangle which has this pattern of singularities, one at a corner and two on the sides. And then the three simplices, the tetrahedra, are these rectangles where you have one singularity on every side. And you should think of these, well, so at least in terms of the motivation for this definition, you think of an edge as kind of sitting there connecting these two things. You think of the face as being like that. And you think of the tetrahedron as being plastered inside this rectangle like that. And I'm purposely not drawing these in because it's actually hard to draw them in and have the whole picture be invariant in a good embedded way. That turns out to be technically an issue in general. But that is the motivation. You want to think of these as kind of pictures of the tetrahedra in my triangulation, and they fit together. There's clearly inclusion relations between them. This, so if you look over at this face, there's an edge of the face and so on. Here's another edge of the face. Okay, so that's the bunch of, that's certainly a heap of triangles, and I claim that this is in fact a triangulation of a three manifold. I write this down on the next slide. Yeah, so I claim these assemble to give a three manifold, which fibers over the leaf space. And in fact, the quotient, the whole thing is invariant by the group, and the quotient gives you a copy of M. So you get a triangulation, an ideal triangulation of M, where what's missing is the, did I say what M is? M is M bar minus the singular orbits. So the singular orbits gave rise to the vertices, and I need to think of them as ideal vertices. Okay. So the end of the story is we get a triangulation. Moreover, this looks a little bit like it might be easy, but it actually is a little tricky. We can embed this thing in the three manifold so that the faces are actually transverse to the flow lines. So so here's a kind of bad picture of it. Here's an edge. Here's a triangle kind of sitting on one side of the edge, and here's a tetrahedron sitting on the other side of the edge, and the flow is kind of passing through these in a kind of consistent way. Here's a kind of profile picture of the same thing. This dot here is now an edge, and there's a bunch of two-dimensional faces coming into it from two sides. There's kind of a tangency structure, and the flow is passing through it like this. That is what this looks like once you build the whole thing. So I'm not going to. It's actually quite a pretty construction, but I only want to get out of it a couple of specific things. But the last thing I want to say about it is that this abstract construction can actually be computed in practice, and this has been done kind of with, for real with a computer and so on, by Schleimer and Siegerman, and various aspects of it were done by Parlak. So almost everything I'm talking about has a very direct computational form, which I am terrible at actually doing myself, but there are people who can do it. So that is the notion of the veering triangulation. And in order to for it to be relevant to us, I want to describe one more thing, which we call the flow graph. So this is a graph in the three manifold, which embeds in the three manifold, so it's also transverse to the, sorry, this is not what I want to say. This is actually wrong, sorry. Transverse to the triangulation. So this is a directed graph. And it's going to be a kind of model for the flow. And what's kind of useful about it is the concreteness of it, the ability to actually compute what's going on. Let me quickly say what the graph is, and then say a few things about it. So it kind of looks like this. Every vertex of the graph is associated to a three simplex, one of our maximal rectangles that we drew before. So here's a picture over here of a rectangle. So that rectangle is associated to this vertex, and then it has three outgoing edges, always three, and they are defined as follows. So if you look at, let me draw a rectangle here. Here's a if you suppose you start with these two singularities, and you start with the rectangle that spans them, and try to find the tallest rectangle that can be built that still spans these two yellow vertices, these two singularities. And it stops exactly when you hit a singularity on both top and bottom. That's the only way it can stop. And so you get one of these rectangles that correspond to a tetrahedron. So that red rectangle corresponds to the red vertex over here. And then there's going to be a green rectangle. If you start with the middle pair and you extend them vertically as far as they'll go, you'll get some kind of rectangle. And finally, whoops, I should have drawn this maybe in purple. There's a purple rectangle, which you get by drawing that one, and that also goes as far as you go. So that gives you, so these three rectangles correspond to the three vertices that you flow up to from the starting vertex. And of course,
so Yair,
yeah.
It looks like you're almost thinking of this as a fat graph, because you have a notion of a middle and then the two on the sides coming from the
That's true.
From the position in the rectangle. Is that useful at all? I mean, is that something we should keep in mind?
I'm not going to talk about it in here, but yes, I think this thing lives in a two-dimensional. So another part of the picture, there's a kind of vertical branch surface, which the triangulation is a branch surface, and there's a pair of vertical branch surfaces, actually maybe stable and unstable branch surfaces that are transverse to the triangulation. And these graphs are embedded in sheets of that branch surface. So part of the analysis involves drawing these pictures in a kind of two-dimensional vertical plane. So yeah, that's actually helpful.
Yeah.
Okay, so that's the graph, and I'm also gonna run out of time very quickly. So let me say a few more things about this. So here's a theorem about this graph. If you look at the cycles of the directed cycles of this graph, every one of them corresponds to some cycle in the manifold. And there's a map that associates to every such cycle a closed orbit of the flow. Or there's a little fine print here. There's something going on with the singular orbits, which is a little different. You have to keep track of a little more information. But anyway, so the cycles of the graph are somehow taken to orbits of the flow by a way which preserves homotopy class. And this map is bounded to 1. So it's finite to 1 with a bound on the number of preimages of any given loop. And it's surjective except for a small set of exceptions which don't account for too much exponential growth. So it's a coding of the flow, which is good enough. It's not kind of complete, but it's good enough to capture the exponential growth rates. And in particular, if you look at the growth rate of the flow with respect to a particular positive cohomology class, that's the same as the growth rate for this directed graph with the pullback of the cohomology class. So you can convert a counting problem on the flow to a counting problem on the graph where there's a little bit more machinery. And this is closely related to symbolic dynamics, but it is not the same. As far as we can tell, this doesn't come out of a standard Markov partition for the flow. Its advantage, I think, is that it's canonical. It depends on the flow kind of uniquely, and is computable as well. Okay, so what do we do with this? let me just say a few more things. So let me first say a few things about counting things on graphs. Maybe this is just notation here. If I have a directed graph, this is just explaining the notation in the previous screen, and I have a cohomology class on the graph, which is positive on cycles for the graph, I can do the same dance as before. I can count the number of cycles and compute the growth rate, the exponential growth rate, and that's the phrase that I chose before, that I used before when I compared the growth rate in the graph to the growth rate in the flow. And there's again a cone of positive classes. And another thing to say is that this cone is polyhedral. All these cones actually turn out to be polyhedral. This cone is polyhedral, and the faces of the cone, that's the classes that vanish somewhere, they correspond to subgraphs. So if you have a cohomology class that's on the boundary of these positive set, that means it must not be positive everywhere. And the subgraph where it vanishes is associated, somehow determines that face of the cone. So there's a nice structure there. And then I think maybe I'll skip this. There's a whole mechanism for computing the growth rates for graphs, which involves taking a sort of generalized adjacency matrix and finding the roots of the appropriate characteristic polynomial. But I'm going to skip that and just say a consequence of it in the 3 minutes I have left or whatever it is. And it's the following fact, which I hope has some intuitive structure. So suppose I have a sequence of positive cohomology classes on my graph. And suppose that this is the following story. There's a subgraph G0. Actually, let me outline G0 in red. So maybe this is the subgraph G0. Okay, and suppose that on the subgraph, all of these cohomology classes are fixed. They're just constant. But there's at least one edge somewhere, here I've drawn it like this, where they go to infinity. So on the complement of G0, all of these cohomology classes go to infinity. So you can think of this as a bunch of metric structures on the graph where some piece of the graph is blowing up. Then I claim that the growth rate of the graph with this sequence of metrics converges to the growth rate of the subgraph with the constant metric on the subgraph. And I think this is intuitively not too bad, not too hard to swallow, because what's going on is the longer this extra edge is, the less it contributes to branching. If you think about how to build more and more cycles, you kind of go around, and every time you have a choice, you go around in different ways that builds kind of exponential growth. So the longer this is, the weaker its contribution to the exponential growth rate. And that turns out to be a theorem. Okay, so there's this nice kind of structure that you can, limiting behavior of certain sequences of metrics on a graph is captured by a subgraph. And then with that, let me give you the last theorem, which is a partial answer to Chris Leininger's question. And it's the following. Let me try to state it. So we have, as before, we have a pseudo-Nassau flow, except now I really want to talk about a suspension flow. So we're back to the fibered setting, but even in that setting, we have something to say. You look at the cone of positive cohomology classes on this flow, that is just Thurston's fibered cone. So this is the cone in cohomology in which all the integer classes correspond to fibrations. And then you look at the same lambda set that we talked about in the very beginning is exactly the set of growth rates of this flow with cohomology classes in this cone that have integer coefficients. That's exactly the fibrations. And the question was, what is the closure of that set? And so here's a statement about the closure of the set. So first of all, the closure of the set is countable, and it's well ordered by the reverse of the usual order in R, which means the limit points are infima. That's what that means. And we can understand the limit points. So if you take any point in the closure other than one is certainly a limit point. That's not hard to see. But if you take any point in the closure other than one, it itself is a growth rate in this more generalized sense that we said. In other words, for every such point in limit point, there is a surface in the manifold, which is dual to some cohomology class in the boundary of the cone. And then if you count the growth rate in the subset of the flow associated to that, the things that avoid that surface with respect to some integer cohomology class, you get a growth rate, and lambda is such a growth rate. So all of the limit points of growth rates are growth rates in this generalized sense, and that kind of organizes. And of course, these things are sort of organized by the faces of the Thurston polytope. And roughly what's going on is that maybe one last thing to say about it, if you take one class Xi that's in the interior of the cone and another class eta, which is in the boundary of the cone, and you just take positive combinations like this, those are points in the cone, and the growth rate of the flow with respect to the class Xi plus I eta, you can think of this also if you want as a Haken sum of a surface with a multiple of another surface. I think that's maybe a familiar object. Those growth rates converge in a downward direction to the growth rate of the sub part of the flow associated to things that avoid that surface. And that's exactly the theorem about graphs. That's where that comes from. So I think I'm out of time. So I will stop there. Thanks.
Thank you very much. Are there questions? Okay, if not, let's reconvene in, I guess, about 8 minutes, right on the hour.